So let's get right into this one. Oh, right. Great. We're going to go right into this one then. Oh. Yeah, we're going to get right into this one. Okay, I'm glad you're concentrating. So, here's the system. Actually, you might note that this is the system that we earlier, wow, way back when, yeah, we wrote this one in operator notation. So, that's the example we're going to look at now. Here it is in its standard form, and this is what we did way back in an earlier example, right in operator notation. So we're going to do our best to use elimination, apply negative d to the bottom, see, and then add it to the top. So what's going to happen is then the y's will be eliminated. So we would get then positive d cubed minus d squared minus d applied to x. No, I'm sorry. Yeah, that's right. And then that added to d of x, right? And that equals 0. No, it doesn't equal 0. It equals e to the t. Oh, what am I thinking? Because there's an e to the t right there. We're taking this and adding it to this one, okay? With doing so, we eliminated the y, but we got a mess of x, but it's not such a mess because the negative d and this positive d wind up canceling each other out. So you get d cubed minus d squared applied to x equals e to the t. Well, that's not so nice, but the characteristic equation you can see is just m cubed minus m squared equals 0. So m has 1 as a root and 0 as a double root. So the solution of the homogeneous equation is c1 times e to the 0, which is 1, plus c2 times 1 times t rather, plus see, this is like the double root 0, and then this one has to have an extra t attached, and then this one is for the m equal 1, right? You understand this? c1 times, well, that's just a constant, right? If the root is 0, e to the 0, but this one, e to the 0, we can't use twice, so we have to multiply by an extra t. So using the method of undetermined coefficients, we posit, oh, that's a good word, isn't it?
Can you get it?
Yeah, we posit an x to the p, or sorry, an xp, a particular solution of the form xp equals a times t times e to the t. See, we have to have an extra t because this this nixes it. We can't just use e to the t, we have to have an extra t in there. So, if we do that, if this is our x of t, then x prime, well, that's easy. The derivative of t times e to the t first d second is t times e to the t plus second d first, that's an extra e to the t, so it's a times t plus 1 times e to the t. X double prime, for a similar reason, is a times t plus 2 times e to the t. And we need a triple prime. Why do we need a triple prime? The answer is, well, look, see? Third derivative. So triple prime, a times t plus 3 times e to the t, and substituting that back into this equation, we get third derivative minus the second derivative equals e to the t. From that we see the 3a minus 2a equals 1. Do you see why that's so? Because 1 e to the t over here, 2 e to the t over here, 3 e to the t over here, so 3a minus 2a equals 1. And by the way, this at e to the t and this at e to the t, of course, cancel out. So, a equals 1. So we've got our function. We know that a equals 1, so here's the solution of the homogeneous plus our particular solution. Wonderful. So the simplest way now, and I am a lazy bum, I admit, the simplest way to find the y, and it also will guarantee only 3 constants, is just go back to the original equation here and say, well, if dy dt equals dx dt plus e to the t, or negative dx dt plus e to the t, or it may be better yet, look, this is y. Y equals second derivative, positive second derivative plus first derivative plus x. Good gracious, that's only going to have 3 constants. Nice. Nice, nice. So the y is not going to be too horribly bad to find. See? The y is going to be, see, here's the second derivative. Remember that? Remember why I'm doing that? Look. Positive second, if we said solve for y equals positive second derivative minus first derivative plus x. So that is what this says. And this is our x. So what we got to do is apply all this. And so the second derivative of this, well, the second derivative of this is 0. The second derivative of this is 0. The second derivative of this is c3 e to the t. The second derivative of this is, we already did that one, t plus 2 times e to the t. Remember, that's how we kind of found the a. And then minus, the first derivative of this is 0. The first derivative of this, oh, minus a c2, then we got a c2. And then minus c3 e to the t. And then minus, the first derivative of this one was just t plus 1 e to the t, so minus t plus 1 e to the t. And then minus this function itself. Here's the function itself. And this simplifies. Let's see how it does simplify. We got this term is the only one like it, minus this c2, minus t plus 1 times e to the t, and then minus this stuff. I guess what happened over here, this c3 e to the t and this negative c3 e to the t canceled out, so it simplified this side a little bit. So now what do we have? We have this negative c2 and this negative c1. So it's negative c1 plus c2. What do we have going on in the e to the t department? Well, we've got 2 minus 1 minus c3. Well, 2 minus 1 is 1, so it's 1 minus d3 times e to the t. What do we have going on in the t department? I think there's a t out there somewhere. Here it is, negative c2t. And then finally, what about the t e to the t department? Well, we've got t e to the t minus t e to the t, so that canceled out. And then finally, we got minus another t e to the t. So we got that minus t e to the t. This is our y. Notice 1, 2, 3 arbitrary constants. So our solution is this, with only 3 arbitrary constants.
All the way.
We did it all the way.